Hi folks, we're going to take a look at the at number 3 from optimization number 2. Okay, and it's a type of question that you would have definitely seen back in grade 10 and 11. So you have an ice cream vendor, finds that producing X cones for sale is given by this equation here. And then you have the usual setup that 500 cones are sold per day at 120. And if you increase or decrease the price by a certain amount, the number of cones sold will increase or decrease always by the same amount. Okay, and we want to determine in the first part the price of the cones that maximizes revenue, and then in B the price of the cones that maximizes profit. Okay, so the way in which you would have solved this back in grade 10 or 11 would have been to let your variable be the number of price increases or decreases, and if that's how you want to solve the problem, that's perfectly fine. But especially in this scenario here, when we have to deal with profit and the cost function is already given in terms of the number of cones, it'd be interesting to see if we can come up with a function for the revenue and the profit given this particular variable. And this is how we do that. Okay, so here we're only interested in the revenue here, so the cost won't even come into play. Okay, and let's remember that the revenue function, okay, if x is the number of cones, okay, is given by, well, the number of cones times the price for each cone. So our price function, again, given by this same variable x, which is the number of cones. Okay, so we're solving this in a different way than you would have seen. Okay, but the thing about the price function here is that it's going to be linear, because every time you increase or decrease by a certain amount, the number of cones sold increases or decreases by a certain amount. Okay, so step number 1 is to find this price function. Okay, so here it's linear, so I need 2 points to determine my function. So I know that when 500 cones are sold, I'm selling them for $1.20. Okay, and here if I decrease the price by 10 cents, the number of cones goes up by 20. So I'll sell 520 cones if I bring down my price by 10 cents. Okay, and from here now I can find the slope. So the slope will just be, well, let's say we go 1.2 minus 1.1, so 0.1 divided by 500 over 520, negative 20. Okay, now if you want to work with point slope form, you can use that here, but since not everybody's using that, I'll use slope intercept form. Okay, so let's determine the equation. So I'll use this point here, so when y is equal to 1.2, okay, the slope is negative 0.1 over 20. Okay, times x equals 500 plus b. Okay, so here 500 over 20 is just going to be 25, so 1.2 equals negative 0.1 times 25 is 2.5. Okay, so b is equal to 1.2 plus 2.5, 3.7. Okay, and so now we have a function for the price. So the revenue will just be x times that function. So here, well, okay, now let's notice I didn't bother simplifying this fraction, but let's take a look here. What do we got? We got 0.1 divided by 20, okay, negative 0.005. So negative 0.005, okay, x plus 3.7. Okay, so my revenue function is just negative 0.005 x squared plus 3.7x. Okay, and I want to determine the maximum here, revenue. Now that works out well since my coefficient is negative, so I know this does relate to a maximum. So you can either go ahead, do your calculus, or if you watched my quick little video, you see that you can determine where this maximum is going to occur using the formula negative b. So in this case here, negative 3.7 divided by 2a, 2 times negative 0.005. Okay, so if you don't know what I'm doing here, you can go watch that other little video. So let's calculate that here. Okay, so the negatives will cancel out, so just 3.7 divided by 2 times 0.005. Okay, 370. Okay. Now since, again, this was a quadratic with a negative leading coefficient, I don't even have to. So in this case here, I don't expect you to check that this is indeed a maximum, because we know a lot about quadratics. Okay, so this is our critical point that leads to our maximum. Let's go actually answer the question. And here it said determine the price. So here I just need to use my price function. So P at 370 is just equal to negative 0.005 times 370 plus 3.7. Okay, so let's calculate that here. So negative 0.005 times 370 plus 3.7 gives me 185. Okay, so the price that should be charged to maximize the revenue for this ice cream vendor should be $1.85. Okay, so a fairly significant increase on his original price. Okay, now let's go ahead and do the second part, which is maximizing profit. Okay, so of course we know that profit, again, in this case here, we'll use X as being the number of cones, is just given by the revenue minus the cost. Oops. Okay, so we already found the revenue function, so that's just negative 0.005 x squared plus 3.7x minus the cost function, which is the one that was given to us. We didn't actually have to determine it. So here it's 25 plus 0.12x plus 0.001x squared. Okay. And now we can simplify this so we can solve the problem. So the profit is given by, so negative 0.005 plus 0.001. So that's negative 0.004 x squared. Here we've got 3.7 minus 0.12, so that's 3.6, so it'll be 3.58 plus 3.58x, and then here just minus 25. Okay, and we notice that the profit function is also a quadratic. Okay, so it really looks like you could have been able to solve this problem even back in grade 10, since everything ends up being quadratic. So again, I'll use my trick for determining the location of the, in this case here, maximum, since the leading coefficient is negative, so it's just negative b, so negative 3.58 divided by 2a, so 2 times negative 0.004. Okay, and let's see what that gives us. Okay, so here we've got, so the negatives will cancel out, I won't bother with it, 3.58 divided by 2 times 0.004 equals 447.5. Okay, 447.5. Okay, and of course that's very interesting because you can't sell 447.5 cones. So the question is, should you round down or up? Okay, now this is a bit of a special example because the profit function is quadratic, and we know that the quadratic function is symmetrical about its axis of symmetry. So 2 points on either side, equal distance on either side of the maximum, okay, will give us the same y value. So here that I choose 447 or 448, well, it should give me the exact same profit. Okay, now say this wasn't a quadratic function where we knew that it was symmetrical about that local maximum. Well, what you'd have to do is check 447, 448, and see which one of those two actually gave you the higher profit. Okay, so here again we've got those two choices. I suppose what you could do is put both of them into the price function and, you know, take it from there. So let's actually do that here. Let's put 447 in the price function. Okay, so let's remember here the price function was, there we go, we got it right there. So let's test that out. So we have negative 0.005 times 447 squared, okay, plus 3.7. So here we get, no, that seems off. I must have made a mistake here. Okay, let's try again. Oh, sorry, I just realized I put it into my revenue function. That would be not what I'm looking for. So let's go back to my price function, okay, which is there's my price function. Okay, so negative 0.005 times 447 plus 3.7 equals 1.465. So 1.465, and then here let's put in 448. Okay, so here we've got negative 0.005 times 448 plus 3.7, okay, which is 1.46. Okay, so either of these prices, so you sort of say, well, they're almost the same. I guess you could charge 1.47 if you're a little greedy and get that extra cent from people, or you can charge 1.46. Okay, you'll end up a little less, but maybe you'll be more competitive. Or you can think that since we're in Canada and we can't really charge 1.46 or 1.47 since things round down. Okay, so here's another little interesting thing in Canada recently, that in the end you'll end up charging 1.45 because we now round down to the nearest 5 cents. Okay, so that's this problem here. So just to recap, you could have solved this whole problem using your variable as the number of increases or decreases. Where that would have come into play would have been with the cost function. Okay, you would have had to have determined whatever expression determines the number of cones and input that into your cost function. So that's what made this problem a little more difficult using the other method for solving. Okay, so I do want to encourage you to consider this other method for